Welcome to Statistical Quality Control. Today we are going to explore one of the most powerful concepts in modern business and manufacturing, Six Sigma. Imagine you run a bakery and your customers expect exactly 10 chocolate chips in every single cookie. How do you guarantee that? We will learn how Six Sigma makes near perfect quality a reality. To understand how we achieve this perfection, let us define what Six Sigma actually is. It is a highly disciplined, data-driven approach designed to eliminate defects in any process. In the real world, making every product perfectly identical is impossible because small changes always happen, like oven temperatures fluctuating or materials varying. Six Sigma is a step-by-step method to measure these mistakes, find their root causes, and fix them, ensuring your process is incredibly reliable. Now that we know what it aims to do, let us look at the math behind the name. The term sigma comes from the Greek letter used in statistics to represent standard deviation, which measures how much your data spreads out from the average. In a Six Sigma process, we squeeze this variation so tightly that you can fit exactly 6 standard deviations between the process average and the customer's acceptable limits. This means your process is so consistent, it produces almost no bad items. Let us visualize the squeezing of variation with a diagram. What you are looking at is the Six Sigma distribution curve. In the center, the vertical line represents the mean or the average process value. On the far left and right, you see the lower specification limit and upper specification limit. These are the boundaries of what the customer accepts. Notice how the bell curve is narrow enough that exactly Six Sigma intervals fit on each side of the mean before hitting those limits. Looking at that curve, pure mathematics says you should only get 0.002 defects per million. But we must account for reality. Over time, machines wear down, workers change, and materials vary. To account for this real-world drift, Six Sigma includes a standard assumption called the 1.5 sigma shift. We assume the process average will naturally drift over the long term. Because of this shift, our theoretical defect rate jumps to the famous standard of 3.4 defects per million opportunities. So we have this target of 3.4 defects. But how do we measure our current performance? We use a metric called defects per million opportunities, or DPMO. This metric tells us exactly how many errors we would make if we repeated our process 1 million times. It is incredibly useful because it acts as a standardized scale. Whether you are baking pizzas or building airplanes, calculating this metric gives you a clear, universal number to represent your quality level. To calculate this universal number, we use a specific formula. The formula for DPMO is D divided by the product of N and O, all multiplied by 1 million. Let us break down these symbols. D is the total number of defects actually found during inspection. N represents the total number of units produced in that batch. O is the number of opportunities for a defect to occur on a single unit. As the number of defects increases, the overall metric increases, meaning the process is getting worse. Once we calculate that metric, we need to know if our number is good or bad. We do this by comparing it to a standard reference table that maps sigma levels to defect rates and yield percentages. Yield simply means the percentage of products that are perfectly good. A 1 sigma level is very poor, with a yield of only 30%. But as you improve to 4 or 5 sigma, your yield jumps to over 99%. The ultimate goal, Six Sigma, represents a near-perfect yield of 99.99966%. Let us see how this works in practice with a concrete example. A customer service call center handles 500 calls a day. A quality check finds 15 calls had errors. Each call has 3 specific opportunities for an error to occur. We need to calculate the DPMO. First, we identify our variables. The manager found 15 errors, so D equals 15. The center handles 500 calls, so our units N equals 500. Finally, there are 3 ways a call can fail, so O equals 3. Now that we have our variables, we can plug them into our formula. We substitute 15 for D, 500 for N, and 3 for O. Our first mathematical step is to perform the multiplication in the denominator. Multiplying 500 units by 3 opportunities per unit gives us 1,500 total opportunities for an error in this specific batch of calls. This means out of 1,500 chances to make a mistake, the team only made 15. Let us finish the calculation to find our final metric. We divide the 15 defects by the 1,500 total opportunities, which gives us a raw decimal rate of 0.01. Finally, we multiply this decimal by 1 million. This gives us a final result of 10,000 defects per million opportunities. Physically, this means if the call center continues at this quality level, they will make 10,000 errors for every million steps. This operates between a 3 and 4 sigma level. Let us solidify our understanding with a second, slightly larger example. A factory produces 2,000 circuit boards. Each board has 50 soldering points, and inspection reveals 23 defective points in total. We need to estimate the sigma level. Just like before, we carefully read the problem to identify our variables. The total defects found is 23, so D is 23. The total units produced is 2,000, so N is 2,000. The opportunities per board is 50, so O is 50. With our variables identified, we move to the calculation phase. We plug 23, 2,000 and 50 directly into our DPMO formula. We calculate the denominator by multiplying the 2,000 boards by the 50 points per board. This gives us 1,00,000 total opportunities. This large number represents every single chance a soldering mistake could have been made across the entire production run. Our fraction now clearly shows 23 mistakes out of 1,00,000 chances. Now we complete the math to find our standardized rate. We divide 23 by 100,000, giving a very small decimal value of 0.00023. We multiply this probability by 1 million to scale it up. Our final result is 230. This means the factory produces 230 defective soldering points for every 1 million points they solder. Comparing this to our reference table, this excellent performance corresponds to approximately a 5 sigma level. You might wonder why we go through all this effort when a 99% success rate sounds great. 6 sigma is crucial because it shifts a company's focus from merely fixing mistakes to preventing them entirely. In industries like healthcare or aviation, 99% is simply not good enough. If a hospital operates at 99% quality, it might drop thousands of newborn babies a year. By aiming for 6 sigma, organizations ensure catastrophic failures become incredibly rare, saving money and building absolute reliability. Let us review the most important ideas we have covered today. First, 6 sigma is a rigorous statistical framework designed to reduce variation and eliminate defects. Second, by accounting for a 1.5 sigma long-term shift, it sets a highly demanding goal of just 3.4 defects per million opportunities. Finally, through careful measurement using metrics like DPMO, businesses can take targeted, data-driven steps to achieve near-perfect quality. You now have a solid understanding of the 6 sigma overview.